I'm Jacqueline. I'm also not Jack in the Discord server, and despite that username, I do also go by Jack. This is my 5th RacketCon talk. Welcome. And today we're going to look at some data structures. But first, a story. So, a long, long time ago, I had a bit of a bad habit of writing too many packages and then forgetting about them. I maybe wanted to learn too many things at once. Who can relate to that? That's about right for this conference. Yeah. But then, I kind of decided this isn't working for me, and I sort of burned out a little on that. It was just a bit too much. Kind of took a little break from Racket for a while, and I sort of needed to come back with a new perspective. And has anyone heard of Dorodango? Oh, yes, we get 2 hands, fantastic. Maybe 3, 4, oh. Anyway, this is a Japanese art of taking just some dirt and clay and very, very slowly shaping it with your hands and polishing it and shaping it more, sprinkling on a little bit more dirt, and just working on that sometimes for years until you end up with what looks fake. Well, totally unrelated to that, I've been working on one package for 6 years and I haven't spoken about it yet. Rebellion is a package I made for myself. It's basically a kind of second standard library, and it's just got a whole bunch of stuff. There's a bunch of like options and maybes, that sort of thing. We got a bunch of collections. I made reducers and transducers, which some of you might have seen, especially in the Discord. I made libraries for concurrency and data types, and I did this. This is what I did. I made a kitchen sink. But today, I'm not going to show you all of it, because we'd be here for hours. Instead, I'm just going to focus on these modules for sorted collections. And to sort data, first you have to actually compare it. So I made a library of comparators, which are just objects that tell you if 2 things are equivalent or one's bigger than the other. And there's even this cute little compare infix macro I made because I actually missed that syntax from Python. Don't at me. And comparators are composable objects. There's a bunch of built-ins for making your own comparators and for composing them together. Here we have a comparator that will let you sort a bunch of precious gemstones, because that's a thing I'd really like to need to do all the time. And the next library, ranges. I made something for, just the kind of ranges and intervals you might remember from math class. They can be bounded on both ends or not. Bounds can be open or closed. You can specify any comparator you want, so you can have ranges of strings if you're trying to do alphabetization or something. And ranges come with a nice little API for doing various queries on them, and you can check if they contain things, if they overlap with other ranges, that sort of thing. And with these, I have made a perfect selection of collections. And if you maybe aren't that fond of that section title, I say objection. First, we have sorted sets, which are like regular sets from the Racket set collection, but instead they keep all of the items in a sorted order. And as you can see here, it is immutable by default, and it supports persistent updates. You can add and remove and get a new set. There's also mutable sorted sets, and that's going to be a theme in this talk. All these collections have mutable variants, but they kind of work together. And you have to explicitly ask for mutability. You don't get it by default. There's also sorted maps, which work pretty much like Racket hash tables, except, again, they keep the keys in a sorted order. And there's both immutable and mutable variants, and they work just like the sets, where you have functional updates or mutable updates if you want. There's also range sets, and this one's maybe a little newer, less familiar. This is a collection of disjoint ranges that all use the same comparator. So here we have a range set that covers this selection of the number line, and there are both immutable and mutable variants. And with range sets, you can express some really useful queries. Like here, you can check if it contains something or if it actually overlaps or fully encloses some other range. And as you can see here, this also works in terms of the range API. So you get all the nice stuff for working with boundaries. Now, how does that actually work? So to implement this, I had to do something I really didn't want to do, which is implement red-black trees. And I don't mean to give you all war flashbacks to your computer science courses, but that is the data structure that you do need to use. And red-black trees, they're a balanced binary search tree. They use node coloring to help maintain some height and variance. That much being said, don't make me explain red-black trees. I'm not going to tell you how they work. There's an 11,000-word long Wikipedia article about it. There's a bajillion papers. There's too many diagrams. It was a nightmare to implement. It's done now. I'm not telling you how it works. You don't want to know. Now, so I implemented mutable red-black trees. And then we had a problem because the persistent red-black trees are worse. Chris Okazaki is a liar and a fraud. He says, oh, it's a perfectly elegant implementation. You've got these nice, he shows a little page long of code for inserting an element. And then when you say, okay, but how do I take things out of the tree? He just goes, exercise left to the reader, like the worst professor that you ever remember from college. It was so bad, people started writing papers about how bad this problem was. And speaking of people trying to solve this problem, okay, so there's this blog post by Matthew Might, one of the authors of that other paper, about well, here's one way you could implement deletion. And he says, let's add 2 new colors to the red-black tree called double black and negative black. Now, who does that make sense to here? Nobody? Good. Because that is nonsense. You couldn't call it blue and green? Who cares? However, this paper was a very nice find. This fellow Cameron at Northeastern University, he isn't here, is he? Okay, well, give him a round of applause anyway. So thank you, Northeastern, for saving me yet again. And he has wrote a paper with a simpler version of the red-black tree deletion algorithm. And it only adds 1 new color, which in the world of these papers is a win.
Is that color also called black something?
I think he went with the double black one. And okay. What?
They're just random terms.
Yeah, they will never show up in any API I ever force you to use. That is a promise. I'm not going to make you type double black anywhere in your code. I did it once. I'll suffer enough for you. So that was enough to make a reasonable implementation for the basic use cases. But I went a little further. And they're not always red-black trees. I made some generic interfaces, and I did some cool stuff. So what is the fastest data structure? Anyone want to guess? I heard linked list, which is obviously wrong. I heard array, which is close. Also close. The correct answer is an array and a bag of lies. So let's talk about collection builders. As it turns out, most of the time when you're trying to collect a bunch of data together, you could separate your use of the data structure into two phases. First, you make it, and then you read from it. If you can do all of your writes up front, and then defer all of your reads to later, you can use a builder. Builders are mutable objects. Just get comfortable with it. And they are write-only collections. You can only put stuff into builders. You can't observe their state. You can't look at them and say, well, maybe add this thing if this other thing's in there. Not allowed. But you can then call a build method to produce an immutable collection from the contents of that builder. And what this will do is, at build time, it will just sort all the data and then shove it into a vector. And it will give you an implementation of the generic sorted set interface that is backed by a vector. So you get all the performance of just working on an array. You don't have to do a bunch of tree operations under the hood to get anything done. And you can still do functional updates on these collections. When you do, under the hood, they will transform into their persistent tree-backed versions. You don't have to know this. You don't really have to think about this. You just need to know that when you do update something that you built, there is a one-time copy cost paid first. Another way I use generics to make code faster instead of slower, which is a nice change, is I made optimized versions of the empty collections. Because in practice, most collections are empty. In a VM runtime, that's more common than you would think, a lot more common. So if you optimize for that case, you can avoid a ton of overhead in a lot of cases. It makes it a lot easier to just pass around lots of collections everywhere that you don't always use. So here we've got two implementations of the sorted set and the sorted map that are specialized for the empty case. And you can see we're taking advantage of generics to just add fast path shortcuts. And this is a really nice example of how to use dynamic dispatch to improve the performance of code. Because people seem to think that you can't do that for some reason. All that said, it's not just about performance. That's not the only reason I made generic interfaces. If that were all I could do with it, I wouldn't have bothered. You can use generic interfaces to make all sorts of more useful, unusual collection implementations. And a view collection is one of them. This is a collection that is defined, it holds its state in terms of a different collection. So they let you reuse collection APIs in new contexts very easily. For instance, you can reverse any sorted set, and it will give you a new sorted set in constant time, because it's not actually moving any memory around. It's giving you a new implementation that is backed by the original. It simply translates all of your API calls into reversed forms. And if you reverse a collection twice, you'll get back the one you started with. Well, I heard a gasp. I appreciate that.
When you say the one you started with, you mean like 1-year quality?
Yeah, it'll be eq. Probably. I'm not promising. It will be equal. You can also adapt one collection to fit a different collection API. For instance, here we can get the key set of a map. And this, like the reversed set, also runs in constant time. It will and now you can use all the set operations on a hash's keys. Like if you just want to iterate those, you can do this and it's constant time. There are also subset views. So let's say if you want to check if a set has any elements less than 10. Well, with collection views, you don't need a new API for that. Instead, you make a subset using the less than range, and that will give you a new sorted set that implements the sorted set interface, which includes a method to check if it's empty. This works on both mutable and immutable sets. And it works on sorted maps and range sets too. If you do sorted submaps, you'll get just the key and value mappings in that range. And if you do it for a range set, you can get just the parts of the range set in a range. And that will like cut off the range boundaries to fit. And I can also make thread safety an extra feature relatively easily. Don't poke at it too hard. There's a synchronized sorted set wrapper where you can give it a mutable sorted set and it will return a new implementation that guards all access through its methods with a lock. There's a couple extra little bits here and there to talk about, mostly about how these collections interface with other bits in the Racket ecosystem. We have for loops. You can do for range set and say a comparator, and it will build the range set for you. We've got this for the other collections too, probably. And you can pretty print them, and it will do the nice, you get some indentation in there. For the range maps, it'll have the keys and the values on the same line. Respects the column width. There's also a stream pipeline system in Rebellion that I am just going to tease you with. I'm not going to go into the details of this. But how it works is we've got this transduce function where you can give it any sequence and a series of intermediate operations that you want to do. Those are called transducers. Then we specify a terminal operation called the reducer, and that will let us transform one sequence into something. In this case, we're turning an infinite sequence, filtering it, limiting it, and then collecting the results into a sorted set. Now, I will give a talk on reducers someday, but not today. We've got enough to do. There are ranges in Rhombus now too. They don't work quite exactly the same, but I just bring this up to talk about how I made this library for myself, but I've been trying to spread some of the ideas around here and there, and some of it's caught on, some of it, maybe enough. So, wrapping it all up, can you use Rebellion? I mean, I'm not a cop. But I did mostly make it for myself. I use it in a bunch of other projects, especially resyntax, which cares a lot about ranges of source code and various operations on that, like to check if you're preserving comments. And I will give another talk on resyntax too. That'll happen someday. If you do use Rebellion, please tell me, because I end up breaking things sometimes on purpose. But if your package is on the package catalog, I can find it and check before I do that. You will have to get used to long build times. Because I made it for myself, I don't really feel like doing all the effort of package splitting. So all the docs and tests are just in there with the regular code. And I'm used to that because I work at Google, and long build times, you just live with it. Now, does anyone have any questions?
So what exactly about a red-black tree makes it so appealing for your use case? Do you just need a balanced, sorted thing? Or like, if you had a RRB tree, would you redo your stuff with an RRB tree?
Oh, so why red-black trees? Why not RRB trees like in the new tree list collection API? RRB trees don't really have a way for user-specified sorting to be a thing as much. And also, I said there were 11,000 words in Wikipedia explaining how these worked. That's a lot more useful than like 1.5 papers if you're trying to implement something. Those diagrams saved me. So ease of implementation, funnily enough, was a factor. And they work. They work quite well. Lots of languages use them. It's fairly stable. I didn't have to spend a bunch of time guessing whether or not this would give me something reasonable. And I didn't really have to like thoroughly test the performance of it to know that it would at least, if it's slow, it's because it's a bug. It's not because I picked the wrong data structure.
So I have a couple questions about range sets. I remember you had kind of a hard time implementing them. So I was wondering if you could talk a little bit about the complexities there. Like, are those also backed by red-black trees? And I'm also curious about the applications in resyntax. You mentioned you use it to preserve comments. Like, what's the exact, why do you need range sets to do that?
So, 2 questions. One, how hard was it to implement range sets and how do they work? 2, how do they work in resyntax? So range sets, I took advantage of the generics and I implemented range sets in terms of sorted maps. Under the hood, a range set is a little wrapper around a sorted map from the lower bound to the upper bound. And that means I didn't have to make a bunch of new data structures just for this. As for how they work in resyntax, comment preservation is probably the biggest one. So does anyone here not know what resyntax is? Okay, resyntax is a tool I wrote that will analyze Racket code and suggest ways to improve it. And you can also just run it on some files and it will just fix everything it finds. It's kind of similar to an auto formatter, except it gives you more structural suggestions rather than just like white space, parens, that sort of thing. And a problem with this sort of tool is that comments don't typically survive into syntax trees. And so if you want to write a tool that rearranges code using syntax trees, you have to make sure that it doesn't drop the comments, because that is not a way to refactor code. Don't do that. So resyntax, when it starts up, it'll find all of the source locations of comments in a file and make a range set saying, these are all the positions in the file that have comments. And if you want to apply a refactoring, it can check what parts of the source code the refactoring would preserve, and it will check to see, okay, we've got all these comment locations and all of these preserved locations. Does one range set include the other? And based on that sort of query, it can figure out, without a bunch of fancy special purpose code, whether or not a refactoring will forget about comments.
So I was curious, particularly with the transducers library.
All right, I'll go back.
Have you looked at any kind of lazy collections with this?
So have I looked at lazy collections? Nah. The way transducers kind of are meant to work is that you can have a lazy start, you can have lazy middles, but the end should drive everything. The reducer can bail out early. Like you can make a reducer that says, I'm only gonna collect 10 elements and then quit. That's a thing. So that sort of laziness is allowed. but this is meant to produce a value.
Hello, Ethan, unaffiliated. I wanted to ask, when you take views into mutable collections, do you have checks for iterator and validation? If I like iterate over a view and then mutate its underlying collection in that iteration?
So I have GitHub issues to implement those checks. That's close enough, right? Right? Yeah, that's how software engineering works. You make a bug report and then you're done. Anyway, so there is some checking for mutable views, and there's two kinds of ways that mutable state interacts with views. You can have a read-through view, which is where you have a view of some mutable state, but you can't mutate it through the view. So, no, I don't have a good example of that off the top of my head. But if you were to mutate the underlying collection, those changes would be reflected in the unmodifiable read-through view. For write-through views, mutations will work in both ways. You can mutate one or the other, and it will reflect the changes. And for those, there's various checks to disallow certain kinds of mutations. Like if you have a sorted map and you make its key set, that is a write-through view, but you can't add elements into it because how would that work? But you can take elements out, so you can use it to, say, delete an entire range of a sorted map by taking the key set, making a subset, and then there's a method for just delete everything from this collection.
Any other questions? Maybe time for one more.
So you talked about optimizing empty collections a little bit. Do you have any optimizations for the representation of those collections, or just for querying the size and stuff like that? I know in Rust, if you make an empty vector, it doesn't actually allocate memory until you put stuff into it.
Alas, Racket doesn't allow me to make that kind of optimization. Would be nice, but it does still allocate an object. However, there's only one object in the VM. There's a reused instance. And it doesn't have any fields or state or anything. Well, it has the comparator, because you do want to be able to get the comparator. It might be one per comparator. I can't remember if I added a weak map or something to do that.
All right, well, it sounds like an incredibly valuable resource for languages in Racket. So thank you, Jack. And